Maps, friend networks, the web, package dependencies, flight routes, they're all the same shape underneath, things and the connections between them. That shape is a graph, the most flexible structure in computer science. A tree is actually a special kind of graph with strict rules, connected, no cycles, and often drawn with a root. Drop those rules and you can model almost anything. The catch? With connections going every which way, just visit everything suddenly needs care. In this video, we'll store a graph, walk it two different ways, and find the shortest path through it, reusing the priority queue from last time. A graph is just two things: vertices, the nodes, the things, and edges, the connections between them. That's the whole definition. A social network, people are vertices, friendships are edges. A roadmap, intersections are vertices, roads are edges. Compare it to a tree. A tree is a connected graph with no cycles. In DSA, we usually draw it with a root, but that root is just an extra way of organizing it. The graph itself doesn't require one. A general graph makes no such promise. There can be many paths between two nodes or none, and edges can loop back into cycles. Graphs come in flavors, set by three choices. First, direction. In an undirected graph, an edge goes both ways, a mutual friendship. In a directed graph, it has an arrow. You follow someone who doesn't follow you back. Second, weight. An unweighted edge just says connected, while a weighted edge carries a number, a distance, a cost, a travel time. Third, cycles. A path that loops back on itself. Cycles are exactly why we can't blindly wander a graph. We'd loop forever. Pick the three knobs to match your problem. How do you put a graph in memory? Two classic options: an adjacency list keeps for each vertex a list of its neighbors, compact and perfect when a graph is sparse, which most real graphs are. An adjacency matrix is a grid where cell row I, column j is 1 if I and j are connected. Checking is there an edge is instant, but it always costs space proportional to vertices squared, even when there are barely any edges. Rule of thumb: lists for sparse graphs, matrices when the graph is dense or you constantly test specific edges. The first thing you do with a graph is traverse it. Visit every reachable vertex. Sounds easy, but cycles make it dangerous. Follow edges blindly and you'll circle forever. The fix is one simple idea: a visited set. Before exploring a vertex, check whether you've seen it. If so, skip it. If not, mark it and continue. That single guard turns an infinite wander into a clean, finite walk. Breadth first and depth first both use this visited set. Dijkstra uses the same safety idea but calls it settling a vertex. Once its shortest distance is final, we never process it again. Breadth first search explores in rings. Start at a source, visit all its direct neighbors, then all of their unvisited neighbors, and so on, expanding outward one layer at a time. The tool that makes this work is a queue. At the start, then repeatedly take the front vertex and enqueue its unvisited neighbors. Because BFS fans out by distance, it has a superpower. In an unweighted graph, the first time it reaches a vertex, it has found the shortest path there. Fewest edges guaranteed. Depth first search does the opposite. From the start, it commits to one neighbor, then that neighbor's neighbor, plunging as deep as possible before it backtracks and tries another branch. You can write it with an explicit stack, but it falls out naturally from recursion. Each call dives one level deeper, and returning is the backtrack. One caution: recursion is clean, but on very deep graphs, it can hit the call stack limit. So an explicit stack is sometimes the safer choice. DFS won't give shortest paths, but it's the natural fit for structure questions. Is the graph connected? Is there a cycle? What's a valid ordering of dependencies? So which do you reach for? Both visit every vertex in linear time, but their shapes differ. Breadth first uses a queue and spreads out level by level. Choose it for shortest paths in unweighted graphs, or anything closest first. Depth first uses a stack or recursion and plunges deep. Choose it for connectivity, cycle detection, and dependency ordering. One explores wide, the other explores deep. The right pick is whichever matches the question you're asking. Here's the twist. Breadth first finds the path with the fewest edges. But once edges have weights, fewest edges isn't the same as lowest cost. A two-edge road might be far longer than a winding three-edge one. So for weighted graphs, we need something smarter, an algorithm that always considers the cheapest route discovered so far, not just the shortest in number of hops. That algorithm is Dijkstra's, and it leans on a tool you already know. Dijkstra's algorithm finds the cheapest path from a source to every other vertex. The idea is greedy. Keep a tentative distance to each vertex and repeatedly settle the unsettled vertex with the smallest known distance, because nothing cheaper can reach it later. Each time you settle one, you relax its edges. If going through it gives a neighbor a shorter distance, update that neighbor. One important condition: Dijkstra works when all edge weights are non-negative, like distance, time, or cost. If negative weights exist, we need a different algorithm. The piece that makes it fast is a priority queue, the min heap from the last episode, handing you the closest unsettled vertex in O of log v time. Watch it run from A. A starts at 0, everything else infinity. Pop A, relax its edges. B becomes 2, C becomes 5. Pop the smallest, B at 2, relax. C drops to 3 through B, D becomes 6. Pop C at 3, relax. E becomes 5. Pop E at 5, relax. D ties at 6. Pop D at 6, F becomes 7. Pop F. Done. Every vertex now holds the true shortest distance from A, and following the chosen edges backward traces the actual path. Let's total it up, assuming an adjacency list. Breadth first and depth first each visit every vertex and every edge once, so both run in order v plus e, linear in the size of the graph. Dijkstra with a binary heap costs order v plus e times log v for all those heap operations. Space is order v plus e to store the graph plus the visited or distance array. A matrix instead makes edge lookups instant but forces order v squared space, worth it only for dense graphs. Graphs are everywhere once you see them. Map and GPS routing is Dijkstra or its faster cousins over a road graph. Social networks run friend of friend and recommendations over the connection graph. Search engines crawl the web as a graph of links and rank pages by it. Build tools and package managers use a directed graph to figure out what must come before what, a topological sort. Networks, scheduling, dependency resolution. Anywhere things connect, a graph and one of these traversals is the answer. In practice, it's compact. Store the graph as an adjacency list, a map from each vertex to its neighbors. Breadth first is a queue plus a visited set. Depth first is the same idea with recursion. Dijkstra is a priority queue of distance vertex pairs. Pop the closest and relax its edges, pushing improved distances back on. In Java, that's a priority queue. In Python, it's heap queue over tuples. The shape is identical across both. The structure you learned does the heavy lifting. To wrap up, a graph is vertices plus edges, the most flexible structure there is. Store it as an adjacency list for sparse graphs, a matrix for dense ones. Every traversal rides on a visited set, so cycles can't trap you. Breadth first explores in layers and gives shortest paths when edges are unweighted. Depth first plunges deep and answers questions about structure. For weighted shortest paths, Dijkstra settles the closest vertex each step using a priority queue, as long as weights aren't negative. Reach for a graph whenever your problem is really about things and how they connect. If this made graphs click, subscribe and tell me what to explain next. Your vote picks the next video.